The lesson today is on the volume of a solid using cross sections. The essential questions for our lesson today are: number 1, how to find volume of a solid using cross sections, and 2, how to use cross sections to prove volume formulas that we have learned in geometry. So at the end of our lesson today, you will be able to answer these 2 questions. First, let's review our lesson from last time on how to find the volume of a solid up revolution. To form a solid up revolution, we started with a region on the xy coordinate bounded by some given functions. We then revolve the region about an axis, let's just say an x-axis in our case here. After revolving about the x-axis, you will get a solid, as we see in the diagram, and it is the solid up revolution. In order to find the volume of the whole solid, we're gonna look at a thin slice of the solid in the shape of a circular disk. We can write the area of a disk as a function a of x using the formula for area of a circle is pi r squared. The volume of the solid is the sum of the area of the disk. So the volume equals the integral of a of x dx. So that's the review of our last lesson. We're gonna move to our new lesson of finding the volume using cross sections. For the solid with known section, we use the same concept of solid up revolution. So let's start with a region on the xy coordinate as we can see here. Now, instead of revolve the region to form a solid up revolution, we're gonna create another kind of solid. If we know the shape of the cross section of the solid, we can find the volume of the whole solid. So let's pretend that our solid has a cross section and the shape of equilateral triangle with one side is on the region perpendicular to the x-axis. So as you can see, all of the cross sections here are in the shape of equilateral triangles. Using the same concept, so we have to find the area of one cross section in a function of x. We call that a of x. Then the volume of the solid will be the sum of all of the area of the cross sections. So v equals the integral of a of x dx. And then you can use the information about the functions given in the problem in order to determine the limits of the integral, and then integrate to get to the volume of the solid. So let's work on an example. The base of a solid is the region bounded by the lines y equals x, y equals 0, and x equals 4. The solid cross sections are semicircles with diameters on the xy plane and perpendicular to the x-axis. Find the volume of the solid. We will go over all the steps of finding volume of a solid using this example. The first step is to sketch a solid and a typical cross section. To sketch the solid, first I draw the xy coordinate. Then I sketch all of the function given in the problem. The line y equals x, the line y equals 0, which is the x-axis, and then the line x equals 4. Then I shade in the region that is bounded by all of those functions. Then I sketch the cross section. The green line shown in the diagram is the diameter of a cross section. And each of the cross section has the shape of semicircle. Couple more of cross section to show our solid clearly here. The second step is to find the formula for the area of a cross section a of x using the diagram in step 1. So the area of a semicircle is 1/2 pi r squared. Using our diagram, we see that the diameter is x, so r is 1/2 x. Plug that into the area. You will get a of x equals 1/2 pi times 1/4 x squared, which is pi over 8 x squared. In step number 3, we set up the volume of the solid equals the integral of a of x, and then we need to find the limits of integration. As we say, the volume will be the summation of all the area, so it is the integral of pi over 8 x squared dx. Checking our diagram again, you see all of this cross-section start at 0 and end at 4, so our integral start with 0 to 4. The very last step, step number 4, all we have to do is just integrate a of x to find the volume of the solid. Now all you have to do is to evaluate the integral to get pi over 24x to the third. Evaluate from 0 to 4, which is 8 pi over 3. Let's go over all of the steps of finding volume of a solid. Step number 1, sketch the solid and a typical cross-section. Step number 2, find the formula for the area of a cross-section A of x. Number 3 is to find the limits of integration, and number 4 is to integrate A of x to find the volume of the solid. We can use the same concept to prove the formulas that you have learned in geometry to find volume of solids. Let's prove the formula for volume of a cylinder that you learned before. We all learned that the volume of a cylinder is pi r squared h, where r is the radius and h is the height of the cylinder. I place the cylinder on the xy coordinate where the origin is at the center of its base. We can see that the x-intercept is at r0 and the y-intercept is at 0h. Using the same concept with cross-section, we're going to cut the cylinder into slices of disc. The area of the cross-section is A of y equals pi r squared because all of the cross-section are stacking up in the y direction. The volume is the sum of all of the area of the cross-sections, which is the integral from 0 to h of pi r squared dy. So now all we have to do is to integrate to get pi r squared y evaluated from 0 to h, which is pi r squared h. And that is exactly what we have learned in geometry. The volume of a cylinder is pi times r squared times h, where r is the radius and h is the height. To end our lesson, I want you to remember the steps of how to find the volume of a solid using cross-section. The very first step that you need to do is to sketch a diagram with all the information stated in the problem. And then using the diagram, you will be able to find the area as a function A of x of one cross-section. Then we set up the volume of the solid equals to the integral of A of x and use the diagram again to determine the limits for the integral. After setting up the volume equals the integral and determine the limits, you can integrate to get to the answer.